The, Dr. Sadiq research interest span power systems, planning, operations, and optimization, utilizing solutions and analysis tools, including Mad Power, PSAT, and MATLAB. He has contributed to international projects, including artificial intelligence for clean energy since 2019. This is a project funded by the Royal Academy Engineering in UK. He is currently working on the Homegrown Clean Energy, which is a project that started since 2024 and we end in 2027. Dr. Sadiq is a recipient of the prestigious award MIT ETT Fellowship 2025 and the 2029 IEEE Industry Applications Society. I take that again. And the 2029 IEEE Industry Applications Society Fellowship. He is passionate.
I guess that was 2019, right?
Yeah, 2019. He is passionate about bridging cutting-edge research with real-world impact. And that is about our noble speaker for today. May we make welcome Dr. Sadiq Ahmad for his presentation.
All right, thank you very much. Can I share my screen now, please?
Go ahead and share your screen.
Thank you. Yeah, so good evening, everyone. I hope you can hear me clearly. Hello, can you all hear me clearly, please?
Yes.
Yes, we can hear you. You're welcome.
I think you need
Thank
to
you.
make the screen big. Are you using two screens?
Yes, we can hear you.
Okay, let me stop sharing and share again. Is it better now?
Perfect, yes, better now. Good, good.
Thank you very much. Like I've been introduced, I'm actually Abubakar Sadiq Ahmad, a faculty member of the Department of Electrical and Electronics Engineering, Federal University of Technology, Mina. I'm excited to be amongst you here. And this evening, I will be discussing the viability of power transfer, particularly looking at the continuation power flow approach. And in my presentation, I will try to describe the challenges in the deregulation and how the conventional tools such as the traditional Newton-Raphson has actually failed. And then the continuation algorithm came to our rescue. I also look at our contribution in the math powers implementation of continuation power flow. And we also go through our application into real world scenarios, and then I conclude my presentation. Now, around the world globally in the last few decades, utilities around the world are actually embracing deregulation by unbundling their entities. This deregulation has ensured competition as well as flexibility in operation. thereby increasing access to electricity, increasing access to the grid. But then this also came with increase in load growth. And also that deregulation increases power transfer transactions, which actually comes with the fact that there is need for open access to the transmission infrastructure. Again, this deregulation also requires secure transfer capability assessment. In other words, it requires non-discriminatory access to transmission network. And so we want to know specifically how much power can be moved from one point to another, and how are we going to be able to know this amount, which is now talking about the assessment, and if possible, we also want to know how we can enhance this. So in a deregulated environment, assessment and enhancement of transfer capability becomes very important. However, this has been complicated a bit, particularly in terms of assessment, with the penetration of renewable energy that are variable and are converter-based, and sometimes they are also connected to the grid, because the operations can be either in grid mode or in islands. And so when they are in island, we also need tools that will be able to help us to assess these transfer capabilities or the required amount of power that can be moved from one point to another. Again, in deregulation, we have said that it requires open access to transmission infrastructure, and this has brought about increased load. Increased access means we have increased load. A lot of people are connected to the grid. However, it means that we need more power to be served to this increased load. So we want to, again, apart from assessing the transfer capability, they will also want to enhance this transfer capability. But then the enhancements would be with industry-rated equipment such as flexible AC transmission systems. So therefore, with this deregulation, we needed tools for assessments and enhancements of transfer capability, particularly for online application, because we need it real time so that market participants can take decisions. However, the conventional approach to transfer capability assessment is the Newton-Raphson algorithm that uses repeated power flow approach to do this. And how does it do it? It tries to linearize the power flow equation around a single operating point, and then do this repeatedly to get what amount of power you can transfer from one point to another. Now, this approach is actually pretty fine. It works well, particularly when the grid or the network you are considering is actually far from stability limit or from thermal limits. However, the Newton algorithm actually fails at the point where you now have increased penetration of distributed generators or renewable energies into the grid, and therefore Newton-Raphson algorithm becomes ill-conditioned and Jacobian becomes singular, leading to voltage instability. But of course, this is precisely the point of interest for us, because the green revolution is actually trying to drive or decarbonize the power supply value chain by increasing the renewable energy penetration. And that means that with deregulation and penetration of renewable energies, power grids are now being operated closer to their limit. And this close limits or close to the limit means that Newton algorithm actually fails at that point. So we needed something that will be used to assess that. And then the continuation algorithm actually came to the rescue. And it does this by parameterizing the power flow equation and thereby avoiding what we call singularity issues. And it parameterized the power flow equation with a loading parameter called the lambda. And this lambda it does by the method of predictor-corrector approach. And then because of this, it's able to avoid the singularity issues even for ill-conditioned network. And so the continuation power flow actually traces the entire roadmap to the points of power transfer. But the continuation algorithm or the continuation power flow needs to respect and dictate limits in order to ensure the viability of power transfer. And this limit, importantly, are the line flow limit, the stability limit, and also ensure that the voltages at different points in the network remains within the allowable voltage limit. But interestingly, those three constraints or those three limitations are actually the constraints to power transfer. And if you look at this equation, it means that in order to transfer power from this point to another point, simply, this is the equation for real power transfer, and this is the equation for reactive power transfer. Importantly, we will look at the real power transfer. You will see that these limitations or the factors that constitute the transfer of power from one point to another are actually constituents of the reactance of the line, which we translate to the thermal limit, the sending and the receiving end voltages, as well as the stability limit, which of course we model as the generator reactive power limit. So one of the work that we did was to improve or develop the continuation power flow implementation in the software called Math Power. And so we developed thermal constraint and voltage constraint and incorporated into Math Power since 2019 or so. Yes, 2018, 2019. And that has earned us a mention in the Math Power documentation, which I have a link here. Because of time, I won't want to go into the link, but it is on GitHub, so you can look up this contribution to the software. Of course, it's also worthy to mention that Math Power is actually an open source power system simulation software. So what we did is to ensure that in Math Power implementation of the continuation algorithm, we were able to enforce the power flow limit on the transmission line or on transformers. We also are able to enforce the voltage limitation at every point or node or buses on the network. I also ensure that we enforce the generator reactive power limit that ensures stability of the network. And these three limits are actually interrelated this way, and we can see by the graph by my right on the slide that the stability limit is actually the most severe constraint, because generators are actually the ones providing power, and they needed to be at that limit to ensure the viability of power transfer. And then the thermal limit, importantly, actually just translates to the capacity of the line, has current carrying capacity, which we can also translate into the MVA capacities and all of that. Now, an important outcome from the continuation algorithm is what is called the PV curve, or what some will want to refer in some texts as the nose curve. And from here, we will see that the PV curve actually comprises of two regions, the stable region and the unstable region. And what it does is actually tries to trace the power flow equation completely. And at the turning point, we have the maximum loading parameter. And that is why they call this curve the nose curve. That maximum loading parameter is actually the maximum or critical turning point, which also translates to the voltage collapse point. Very importantly, in order to ensure viability of power transfer, we want to operate the system or the power system network on the stable region. So we want to zoom into the stable region. In the stable region, we also again want to ensure that we are operating the system to ensure viability of power transfer within the voltage stability limit, thereby avoiding the voltage collapse point. So having said that, we will now look at how we use the continuation power flow approach to be able to ensure viability of power transfer transaction, particularly the assessment and enhancement of available transfer capability in the network. First, by definition, the North American Electricity Reliability Council, NEC, defines available transfer capability as the energy remaining in the physical transmission network for future commercial activities above already committed uses. Mathematically, it actually means that ATC is actually equal to the total transfer capability less the transmission reliability margin, and also less the sum of capacity benefit margin and the existing transmission commitment. If you look earlier, one of the graph I showed us was relating this stability limit, voltage limit, and thermal limit. And here we have now combined those limitations and the definition of NEG to what transfer capability entails. So our job, in order to ensure viability of power transfer transactions, is to map the NEG definition as well as the stability limit to the continuation power flow approach, or the nose curve, the stable region of the nose curve of the continuation power flow approach. And we will try to map each of the terminologies in NEG definition to the graph by the right, which is actually from the continuation algorithm. So first, let's look at what NEG calls the existing transmission commitment. This actually translates to the normal operating points that we have earlier, and that is the base case scenario. This is where we are, and we want to move ahead to see how much power we can move further without actually compromising the three limitations to power transfer. Again, we will see that the total transfer capability by NEG definition actually translates to the voltage collapse point, which we don't want to operate the system at, because operating the system at voltage collapse point entails that we may try to lose some loads, and we can also throw the system into instability. Again, we will look at the transmission reliability margin. By definition, there are a lot of approaches that are used in computing or assessing the transmission reliability margin, but it is actually an offset from the voltage collapse point in order to avoid operating power system network at instability point. And lastly, the available transfer capability is actually the difference between the normal operating point and the transmission reliability margin, which is an offset, as I said earlier, of the voltage collapse point. So in order to demonstrate this approach, we look at a simple AC transaction using the Western System Coordinating Council's 9-bus network, which some also will want to refer to as the IE 9-bus network. And here, we try to simulate the load increment as demand bit. As you can see, the 9-bus network, we have load at bus 5, 6, and 8, and we have generators at bus 1, bus 2, and bus 3. So we are looking at a scenario where this bus increment at bus 5, 6, and 8 will be supplied by any of these generators, or what we call the supply bits. It's either only one of the generators is supplying, or generator 2 is supplying, or generator 3 is supplying. Or we have a case where 2 out of the 3 generators want to supply the increment in this load, or we have a case where all the 3 generators will be supplying the 3 increase in load. So this approach, as I said earlier, was part of the work we did as far back as 2019, and we have published this in the Journal of Electrical Engineering and Computer Science. And this is actually what we developed, the approach, the framework of what we use in ensuring viability of power transfer is shown in the flow chart here. And the upper part of the flow chart actually is for assessment of the ATC at base case, and the lower part is actually for ATC enhancement. And we develop an approach called the hybrid of real power performance index and particle swarm optimization to do the enhancement. Again, we also went further to go above the simple network to now create what we call a synthetic integrated transmission and distribution network. Here, we went ahead to have about 48 nodes of distribution network, because we are now talking about deregulation, which encompasses an integrated transmission and distribution network, and thereby allows us to simulate an integrated network, not necessarily separately looking at transmission or distribution. And so here we now have about 56 or 57 bus network that we use to simulate that. So here, in order to place our fact, I said earlier, a hybrid of real power flow performance index and particle swarm optimization. And these red lines or red boxes actually depict the possible locations where we can place this equipment for transfer capability assessment. And here we have a surface plot that tells us how it looks like and what are those points that we can use to place these equipments on the transmission network or the transmission section of the network for enhanced transfer capability for different type of fact devices, as well as different type of power transaction. and we look at the assessment and enhancement with TCSC. TCSC is actually the Taristo Control Series Compensator, which is a series type of fax devices. It's among the first generation type of fax device. And we also look at the Static Synchronous Series Compensator, which is now a second generation type of fax. There is also a voltage source converter type of fax. And we can see that for different type of transactions, we have different amount of power that we can transfer, which ensures that we know how viable certain demand bits are in the transmission network. Again, when we try to implement for different type of fax, like I mentioned, with TCSC, SSSC, we try to see to ensure that the system remains stable, respecting voltage constraint, respecting thermal limit constraint, as well as stability constraint. So here we look at the fact that for each transaction or for different transactions, what is the voltage profile? Are we still operating within the allowable voltage limit? And for all transactions, we can see from each of these graphs that our voltages are still above the transmission network. I think I have some messages here. Okay, this is not for me. So at this
Please
point,
don't bother with the
confirm.
messages. Yeah, if there are any questions in the chat, I will ask them directly when you're done. Thank you.
Thank you. Thank you. But you can still hear me clearly, right?
Absolutely, yes.
Thank you very much. So I was talking about the fact that even after implementation, we want to make sure that what we are implementing, the power transfers that we are implementing are still within the constraints of voltage limit, of thermal limit, as well as stability limit. So here, for about 6 transactions that we looked at, all of them are still below or above the minimum voltage operating range of 0.9 per unit. For different type of facts that we looked at here, we are reporting results of the Taristo Control Series Compensator as well as the Static Synchronous Series Compensator. As I mentioned earlier, TCSC is actually a first generation type of fact, less costly, but with powerful impact on the transmission network, particularly for stability studies or stability improvement. Going forward, I mentioned that we actually develop an approach that we call the hybrid of real power flow performance index and particle swarm optimization. So we also wanted to check to know how good is this approach, how fast it is in terms of the convergence characteristics. So here, for different transactions, we try to compare our approach with the conventional particle swarm optimization. And we can see that because the PIPSO is able to reduce the search space, it is able to obtain a higher or avoid local optimas by obtaining higher transfer capabilities, and also is able to converge faster. In other words, it converges faster compared to the conventional particle swarm optimization. But we will see where its weaknesses also have, and this is what we are actually working on as a research group. Again, the convergence characteristics here shows the difference between the approach that we have developed, which is PIPSO, compared to the particle swarm optimization. I mean the conventional or traditional particle swarm optimization. For transaction T1 that we defined earlier in the table, you can see that all particles are actually converging to one optimal point after about 100 iterations. But in the case of particle swarm optimization, the traditional one, some particles are still at different lines, while the optimal point is actually here. And so we observe this for different type of power transactions that we look at. Now, in order to also ensure the robustness of the approach that we have developed, particularly in ensuring viability of power transfer, and because we are targeting the deregulation, the deregulated framework of power operation, we also wanted to know that what is the time it takes for the approach that we have developed to convert, right? So we looked at the time in seconds for any of these transactions. And importantly, we report that each of these transactions have different time of convergence. And here, the time of convergence can range from about 50 seconds up to 150 seconds or so. But this is actually a bit on the high side, right? Because in real-time applications, you don't have luxury of a minute, right? So this is actually an important question that we're asking currently. And we are saying that can machine learning models actually improve this computational burden as well as the computational time? And this is because for online application required by the deregulated market, you need these things fast for system operators, for system planners to be able to take these decisions and post the real-time transfer capability values for the supply and demand bits can actually be taken and executed. So in conclusion, I would like to share with you our research direction, which we started at MIT, and first by defining what the problem is. Yes, we are able to use continuation power flow to approximate the assessment of transfer capability. However, it comes with some computational burden that is not yet suitable for online market application that is required of a deregulated electricity market. So the solution we are now proposing is to get a surrogate model that is going to relate transfer capability with VAR devices such as facts, and then we are going to develop a machine learning model of this surrogate model that will now be able to estimate this transfer capability faster. And so we will be able to test whether the surrogate or the machine learning models of the surrogate model can be able to meet the requirements of the online posting of transfer capabilities that are required in a deregulated electricity market. So thank you very much for having me. I hope you got the gist. Thank you.
Thank you very much, Dr. Sadiq. Really appreciate that wonderful presentation. Very timely too. Can we, yes, I can see some virtual reactions. Can we use the reactions button to give a round of applause for Dr. Sadiq, please? I did ask before that we can post our questions in the chat. If you did want to do that, but now it's time to ask your questions. And I think I'm particularly, impressed with this presentation because this is, again, because I think that power is Nigeria's greatest challenge. So it is really fascinating to see people working on the potential that we have a deregulated power sector, which I actually think is coming online these days. So impressive work. Before the questions start coming in, may I shamelessly plug in our conference again. I think this is the kind of work we would want to present to a wider, more technical audience that might actually have better appreciation of the efforts we've put in here. So I would strongly encourage you, please. We can take this offline if you need more information so that both yourself and maybe doctoral students or postgraduates working with you or those in your network, I would seriously encourage you to please submit an abstract for our conference. We do need those abstracts coming in. And for every other person on the call, we have some good news because we've got some funding to support students who are traveling for the conference and who are submitting an abstract. So we haven't yet announced how much that's going to be, but anyone who's a student who's traveling for the conference should please get in touch with us or submit an abstract and email us. We'd also be having fantastic prizes for best paper awards and stuff like that. While we are waiting for the questions to come in, please, if you have a question, use the reactions button to raise your hand virtually, and then we'll let you in. So if you do have a questions, please let us know, raise your hands or ask in the chats. While we're waiting for more questions to come in, I just I wanted to pick up a bit, Dr. Sadiq, on the machine learning aspect that you mentioned. I was just wondering, I know it's part of your future work, but I was wondering if you have considered, because of the computational requirements you mentioned, if you have considered training offline and then running inference online, which I think, especially in the age of large language models, is what a lot of people are doing, especially, if you're using reinforcement learning and stuff like that, whereby you train on offline and then you can run, you can deploy it to run inference online in a controlled environment, and then you see how that's performing, so you can know whether that's fit for purpose.
Yeah, thank you very much for that. Yeah, we thought of that. However, we are actually starting with a supervised learning model, but it will be good to also look into what you are saying, to do training offline and then come and do some reinforcement. Yeah, so I agree with that.
Okay, do we have any questions? Please, feel free to raise your hand and come in.
And Kelechi, sorry, before you go ahead with the question, just to jump in on the funding you talked about for student participation for our conference. The funding covers the conference students. So whatever the conference registration is at the moment is £50 for postgraduate and £30 for undergraduate students who are funding covers the registration.
Thank you very much for coming in on that, Mr. Chairman. I hope do we have questions, other ESCO members, please do keep an eye on the chat. One thing I tend to avoid asking questions about, okay, yes, Professor Efika, can you come in, please?
Hi, Engineer Dr. Sadiq. Can you hear my voice properly?
Yes, we can.
Yeah.
Thank you for a very wonderful presentation. The quality of your research outcomes speak for themselves. I wanted to ask a question specifically about your baseline model. In one of your slides, I believe it was maybe slide 20, you showed the IEEE 9-bus model, which is a very reduced model, often focused on sort of academic studies, right? The other models which tends to be used once you start developing these detailed models for transmission constraints forecast tend to start to look like the sort of GB reduced model or the GB zonal 36 bus model. Have you come across something like that for the Nigerian electricity network, or is that something you're struggling to obtain, which is why you reverted to using the 9-bus model?
Yeah, thank you very much for that question. And I think I expect this question actually. Before now, as far back as 2012, 2013, we were actually struggling to get the Nigerian grid model, and it was a bit very difficult. But the good news now is that recently we got an updated version of that with the new IPPs, with the new Zungeru power plant and all of that. And so, but before now, like I said, it's actually very difficult to get this data of the Nigerian grid. But I'm happy, like I said, we now have that data that is courtesy of Professor, the then NEC chairman, the Nigerian NEC chairman. Can you remind me, Professor? I think he's actually in Harvard. Yeah, he was chairman of NEC. So Professor Momo, yeah, Professor Momo.
Yep.
And during his time at NEC, he actually engaged some our researchers back home to get some of this grid data. I'm also happy to report that currently we also submitted national research funded by TED Fund to actually do a model of the Nigerian grid, particularly to study the consequences or the causes of the incessant grid collapse. So we will be improving on the model also that have been worked on by Professor Momo, because since then there are some other transmission expansion plan funded by World Bank that have come up in the country. But even with that, there are lots of instability issues, and within 20, 30 days, we will have 3, 4 voltage, national collapse or grid collapse and all of that. So that is why we felt it is worthy to really get this data, to do some field measurements, to standardize and validate this data and relate it to what is obtainable in the field, and see how we will be able to replicate or reproduce these collapses so that we can get the mitigation solutions. Yeah, so thank you.
Thanks for that, Engineer Dr. Sadiq, and I'm really, really happy that you've moved on from the 9-boss model into Professor Moma's model. One thing I would probably encourage you to do is that it's my understanding that that model that Professor Momo empowered a local team to put together was later on handed over to a company called, I believe they're called Fitchner. Fitchner, who was at that time working with TCN to help them produce an equivalent of the GB36 zonal model, so that they had a bit more resolution in their operations. Now, obviously, I think Fitchner's tenure has also come to a close. And between TCN, the NDPHC, and Fitchner, would have handed that over now to the Siemens team, who's helping out with the PPI, the Presidential Power Initiative. So I think I'll encourage you to look into what's been done so far. Now, obviously, if Professor Moma's model is the most still remains the most up-to-date version, then that's fine, right? And then you can take that and improve upon it. But if some entities like Fitchner or the Siemens Energy team, engaged by the PPI, have updated it to reflect the realities on the ground, then obviously you don't want to do work that's redundant, right? You want to take that model and then add your own insight into it, and that becomes, I guess, a closer to truth version of the system you're trying to optimize. Feel free to reach out to myself. Again, I have to highlight really great work you've put out there. Your research outcomes speak for itself. But yeah, do reach out. I'd love to exchange some thoughts with yourself, and it's an area I'm particularly interested in, especially when you start to tie this transmission constraint model with some of the more commercial market models.
Okay, thank you. I will want to get your mail, right, Professor Ikenna Bruce? Okay, I'll reach out to you.
Yes, we will be happy to facilitate that exchange, and this is one of the things we do at the branch, making sure that our best are putting their minds together to help the country. Thank you very much, Professor, for your contribution. There are a few comments and questions in the chat. I'll take just a few. I haven't seen any other hands up. So one says is actually asking if more load means breakdown of the transmission system. And then the next question says that it is clear that CPF helps identify maximum loadability before voltage collapse, integration of renewable, managing congestions and ATC and C losses, etc. The question is, how can we deploy this to the Nigerian power grid system? So I'll let you address the two questions, and then we'll take more if we have time. Thank you.
Okay, thank you very much. Yes, increase in load actually without a corresponding increment in generation or power transfer to those load actually means a breakdown, because you have frequency distortions. When you have usually in power systems, you must have a balance between your generation and load. In other words, what you generate is actually what you have to consume. And so when you have that imbalance, particularly the scenario that you have painted, where you have increase in load, you tend to have a degradation in your frequency. So that's what it means. And that's why we're trying to ensure viability of whatever increase in load, to see how we can also dispatch or redispatch our generators to supply those increments in load. So hope that answers the question. And the other question is, how can we deploy this to the Nigerian power grid system? Yeah, the first point, which is what Professor Ikenna tried to point out, is get the network data and build the network so that we have a similitude of what is actually happening in real time on the network. And if we're able to get that right, then we can test anything, we can deploy anything, right? We can deploy anything to see how best to improve on the network. So the first point is what we're looking at is to get the real data and model it to depict what actually is happening on the ground. Hope that answers the questions too.
Thank you very much. I think I saw a thumbs up from Simon acknowledging that answer. And I'm going to follow up on that question actually, because I think maybe I might speak for others when I say that the presentation is at a rather high technical level. So I'm going to ask the question that I hope is on everyone's mind. The question being, how does, this affect the price of Gary in the market? What does this mean for, for our system, our grid system? That's on the one hand. And then on the other hand, because your last answer kind of suggested having some sort of test bed. So how do you ensure that there's fidelity, between translating what you've done in simulation or modeling to the actual power system? I imagine there might be some, gaps between that, but how are you accounting for those, and what does this really mean, the entirety of what you've presented and working on? What does it mean for our grid system? How does it affect every other person here? Thank you.
All right, thank you very much. So let me start with what that means to the real investments or the monetary or financial aspect of it. First, the Nigerian power, let me paint this scenario. As far back as 2024, we were meant to understand that the installed capacity of the Nigerian national grid is a little above 13 gigawatts, that is 13,000 megawatts. But the maximum we can do or we have ever done is around 5,200, 5,300, right? And that means that you have generating companies that are fully ready, of course, because they have been privatized. You have generating companies that are sitting idle and are losing funds, are losing revenue because they have generating units that are good to go, that can generate, but they cannot inject into the network. So daily, they are losing hundreds of millions of naira. Just some weeks ago, about a week or two ago, I was at Zungeru Power Plant. They have 4 generating units. Each of them is around 175 megawatts, but only 2 of them are operating, right? And they are actually in business, right? So the point we are making is what we are trying to do here, ensuring viability of power transfer, is how do we ensure that we can evacuate what the generators are generating? And evacuation actually means taking it to where the load centers, where it will be used, right? That is ensuring viability. And if we are able to do that, it means we will curtail the revenue losses to generating companies. We'll increase the revenue to the distribution companies, and that will also impact the industrial revolution that we actually all seek, because currently the cost of diesel is actually high, and that's why a lot of companies are actually are folding up. Can you remind me of your second question, please?
Thank you. Fantastic answer for the first question. The second question was about how you ensure fidelity between modeling or simulation to having this translated into real life projects, especially if you don't have a test bed, or if hopefully you have funding to build a test bed.
Yeah, so it's actually an issue of concern, and that's why we have tried to approach the National Research Fund, TED Fund in particular, to actually fund some of these researches. And you agree with me that usually there is digital real-time simulators that you can build, particularly hardware in the loop and all of that. However, in power system, actually, we often work with computer simulation and try to see how accurate our models are because you cannot do test beds on real high voltage systems. And that's why we do also hardware in the loop test or digital real-time simulators. So, but of course, in order to build those even hardware or DRT TS, we needed funding. And these fundings actually cannot be done by universities or individuals, that we have to approach funding bodies, and which is what we have tried to do for the past few months. Yeah. Thank you.
Fantastic. Thank you very much. And may I again join Professor Ekena to say that this is impressive work, and again to plug in our conference because I think that this work needs a wider audience, and we've got really important stakeholders who would be coming to the conference. There was a question that came into the chat while that answer was going on. Someone is asking if material degradation or failure is one of the root causes of grid outages.
Yeah, so if you ask the NSE industry, that is Nigerian electricity supply industry stakeholders, they will agree with you that yes, equipment failures is actually one of the causes of grid outages. However, the question I often ask is, while we know that those materials or those infrastructures are obsolete, let us reproduce what it is. Let us see how that happens, right? But most times, the grid failures are actually due to simple imbalance in generation and demand that led to skyrocketing of our frequencies or degradation of the frequencies. So it seems generic to always say that our equipment are obsolete and all of that, but we need empirical data. That's the point I'm trying to say. We need empirical data to that, yes. I mean, we need scientific proof rather than just saying that our equipment are obsolete. Yes, particularly at the distribution voltage level, we have that problem majorly. But often these problems are actually happening. The grid outages are actually happening at transmission voltage, which points to a lot of things. First, it will be the imbalance I mentioned. And second will also be the voltage issues, particularly in the far north, where you have long distances and all of that. Or probably you have towers falling down like the burning KB lines and all of that. So yes, it's generic to say yes, degradation or obsolete equipment are responsible, but we need scientific data to prove that.
Fantastic. Thank you very much again, Dr. Sadiq. I don't think there are any other questions in the chat, and I can't see any hands up. So I'm going to invite the branch chairman back I think there's just a comment that has just come in. I think it's more a comment than a question. So we're going to move on. Just a comment from myself, and I've seen this a lot with highly technical people. When you present it to audiences like this, please tell us why first. I really appreciated that answer about the monetary side of things and the human impact on industries and everything. That humanizes all of those power flow equations. So that's a fantastic presentation, and thank you very much.